Special thanks to these companies for being long-term partners of this channel.
Hey everyone, welcome back to the channel. If you're new here, my name is Zach. Here we talk about overlanding, tech, DIY, different types of videos. Today we're going to be doing something kind of special, a little bit unique, and we're going to be cutting up the plastic in your dash to fit 6 rocker switches in a sort of budget switch controller system. So with that being said, we're just going to take that apart or take it out of the vehicle. We're going to take that inside since it's freezing outside, and then we'll walk through kind of how I cut it open and then what we're going to put inside, as well as just kind of walk through a little bit of the wiring, how I understand it best. So thanks for tuning in. I hope you like what I'm doing on the channel. If you do, consider subscribing. Consider liking this video if it brings you any sort of value, and I hope you stick around because I think the content we make here about overlanding is pretty sweet. So let's jump right in. We're pulling out this piece of plastic right here, and I've gone through how to remove this before, so I'm not going to cover it in detail. If you have any questions, just comment below. But what you basically do is you start out by grabbing right here on both of these knobs. This is held in with plastic clips. So you pull this out, and then there is a electrical harness behind here that you need to disconnect. Okay, so that's gonna be dangling just like that, and that's okay. This is held in by a clip and then this electrical plug. I have not clipped that in a while because I keep removing this, but just to see on the back here, you've got this little hook here for the clip, and then you've got the electrical plug there. So we take that off, and then you're going to untwist both of these knobs because we need to remove the center console. So unscrew these, and then just get some pry tools on the sides. Otherwise, I just grab it typically by this like weird rectangular section in your cup holder area that no one knows necessarily what to do with. If you just grab there, this whole thing is held in with clips as well. Don't pull it up too high though, because you're going to need to unclip your seat heaters if you have them, and I think also the rear window goes through that plug. So once you pull that up, there's just this pesky little plastic piece here, which is sitting in between, and it's held in with one little clip here, this white clip, and you just need to pull it up, and then that allows you to fully remove this plastic piece. So the plastic piece that I'll be showing multiple times throughout the video has 4 clips on the back. They clip in here, 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 and then right here. And they have 2 screws that go into these 2 spots right there. So we just pull out those 2 screws and then the 4 clips, and that's all you got to do. It pulls right out. It's honestly really quick. I've gotten to the point where I memorized where all the clips are, and probably takes 2 minutes to pull the piece of plastic. So it's super easy if you know what you're doing, and if it's your first time doing it, it's going to take just a couple extra minutes. It's not a difficult piece of plastic to remove. And as you can see here, while I've been working on the switch system, I've just left that out of the vehicle and used the rest of it like normal. So my climate controls all still work fine, and everything down here still works fine. So it's been kind of handy. I've just got a little hole there in my dash, but everything still drives completely the same and everything. So you could work on this for a period of time and not have any issues. So, all right, it's cold outside. Let's jump inside and start looking at this piece of plastic. Luckily enough, I've seen a couple of forums about this online, but we've got this 6-gang switch thing. I don't even know what you call this. These switch holders that a lot of people will mount right in here in this lower section. But honestly, it's actually better to put it up here, in my opinion, because this cutout space in the plastic, I think, is super useless. Like, I don't know, it's just tiny. It can hold a couple cards or some things. I know some people shove their wallet in there. Totally fine if you like that, but I just didn't think it was that helpful. And then over here on the side, like I said before, we have this USB and auxiliary port, as well as a cigarette lighter port. Now, it's all fine and dandy. I don't mind it, but basically we want to just take that out, and we're going to add in this switch system. The other awesome thing is you can follow exactly what I'm doing. You can do your own thing. I'm just sharing my experience.
But if you needed a 6-switch setup here, you could totally set this up your own way to be a switch controller. Just like, you know, if you didn't have a Switch Pro like me, you could put 6 switches in here and it would be super sweet setup. So we've got a blank switch here. We've got a USB adapter from Blue Seas, which is a 4.8 amp output. That's almost equivalent to a fast charger for most cell phones. So this is gonna be super awesome. And then we've just got a single on-off switch from Blue Seas here. And then I've got 3 switches coming that will go in here that have little stickers included for representing what the switches do. And so I just bought this Blue Seas switch because I wanted to compare them. And then if you were more of a purist as far as buying high quality electrical components, you could buy a Blue Seas switch. Or if you didn't really care and you just kind of got like budget stuff, I think these Amazon switches are gonna be fine too. So we're gonna cut out this plastic a little bit more just so that this will drop in there nice and flush. And then what I'm gonna do is just put a bead of JB Weld all around here so that we can glue this into the plastic and we're not gonna have any issues with it sliding around. So you also may be wondering what this blank tile here is going to be for. I'm going to drill out a hole perfectly in size so that we can drop in a little port for the front plug-in of this Midland radio. So it's gonna be super easy to plug in my handheld right on the far left, and then that cable will just dangle and then go up to the top of my, you know, head unit area where I've hung my mics in the past. So that's what this blank switch is for. This will be for charging stuff. And then we're gonna have 4 extra switches here, which I don't plan on wiring up immediately because it's nice to have flexibility for the future, but I do at least wanna fill them all so that it looks nice. As far as understanding just a little bit of the electrical here, these USB ports are typically in on all the time setup. So you would feed the positive side of this from your Blue Seas fuse box, and then the negative would just go to ground. If you wanted, you could always add a switch in line with the power to this. So if you put a switch before the positive, then you could have a switch that controls the power to this. And so if you wanted to turn off the power, then you could. I think it might be kind of handy to have this with power fed to it all the time. Obviously you want to be careful so that you don't drain your car battery, but especially if I do a dual battery setup in the future, you know, I'd totally be fine with this having power all the time. And then these 4 switches I'll wire up in the future. If we look at this particular switch from Blue Seas, they do send a nice little schematic here. So the top port is ground, the middle is power, and 3 is load. What that essentially will mean for my case is the power is a positive power from somewhere, either the battery or a fuse box or something. Just kind of depends on how careful you want to be. I think if it's really low power, you could just run a power straight to it. It is low power, but I'll probably run some sort of power to this switch off my fuse box. The load is going to be the relay because these switches are going to control relays. And then this will be your typical ground where you screw it into some sort of bolt on your frame. So that's how these switches work. They're pretty simple. And if you're trying to do one of these 6 switch setups, I think this is going to be a pretty sweet budget option. I just showed you everything about this switch system, right? So this is what we're probably going to be putting in. Now this is a typical rocker switch. This is the USB adapter. Keep those things in mind because I'm going to kind of use them in this example. Now, if you're big into DIY like myself and you aren't super familiar with wiring, you've probably been doing a fair amount of research as to how it works. Now, this is not a channel where I'm just going to teach everything because I can't afford that liability. And this stuff is no joke, honestly. Like, if you don't feel comfortable enough to do this, or you're really skeptical of your ability, then be very careful and have someone help you that knows what they're doing. If you're on the fence and you have some confidence to where you think you can do it, just continue to do a lot of research. So I wanted to compile all of my research into something sort of succinct and information I've read online. So let's jump right in. All I'm going to be doing is explaining all of the research I did to wire this stuff myself. I'm not explaining or telling you this is the correct way to do it. I'm not perfect and there may be things I miss, but I want to explain everything that I feel like I understand from the research that I've done. Every single piece of equipment, lighting, everything is different. So you just need to make sure that you do the proper research so that you can do your setup safely, because vehicle fires are no fun. They ruin a trip and they can be incredibly dangerous. So just, this is just my safety warning that this is just another piece of information and kind of me explaining my experience, but this is by no means a tutorial on how to do this. Let's just jump right in. I drew up this simple example, and it's not how you would wire something, but I think it's a nice way to start picturing some of the concepts here. So if you've taken any sort of physics classes, you may remember some of these equations, but I want to start off by explaining them. So the nice thing is vehicles are wired completely in DC current, which means that there is a zero frequency for the electricity flowing. If you remember, like any sort of typical sine wave, it's like this is an alternating current. But with DC, it's a set frequency. It's a frequency of 0. That actually simplifies a lot of this. And so now when we look at DC electricity, a lot of the equations get very simple. We basically have voltage is equal to current times your resistance. And then the power of your circuit or piece of equipment is going to be equal to the voltage times your current. So, and to just remind you what each of those terms mean, voltage is kind of like electrical pressure. And what I mean by electrical pressure is it's how hard electricity is pushing from one side to the other side of, let's say, a light bulb in the middle. So in a typical circuit where you would connect one side of your light bulb to a battery and one side of your light bulb to the ground, what's going to happen is there's a lot of pressure on this side from the battery and there's no pressure on this side from the ground, so all of that electricity is going to push straight through. So voltage refers to that pressure. And then current is the amount of electricity that flows through the light bulb. So based on how hard you're pushing, if you have a lot more voltage, then you're going to push more current. Does that make sense? And resistance basically refers to how your circuit prevents that electricity flowing from your voltage source to ground. So in a given amount of time, it explains how much current flows to the ground. Because if it's just a wire, then you're going to have tons and tons of electricity flowing depending upon that pressure. But if it's some sort of resistance, it's not going to flow quite as much current. It's going to take a little bit of time. For example, let's just say you have a river, and for the river, one river is deep and one river is really shallow. If you have the same amount of water coming from your source and you have a shallow river, it's going to take more time for that water to flow. Let's say your river is the same width and it's shallow. But if you have a really deep river, a lot of that water can flow really quickly. It's kind of similar with resistance. Okay, so just to reiterate, voltage is that electrical pressure, current is how much electricity is flowing, and resistance is how much is pushing against that electrical flow. So what I've drawn up here is just kind of a simple situation. We've got a 12 volt battery, or your car's battery, and then we have a light bar and let's just say 2 ditch lights. So I've used an example here of a Diode Dynamics 30-inch light bar. I forgot to write in 30. And then we have an SS3 pod and another SS3 pod. I'm treating these as sport pods. Now the first thing to mention here, and I've drawn it up this way on purpose, is when we wire up different accessories to the vehicle, they always need to be in parallel. They're not going to be in series. Because what happens is if you have everything in parallel, the voltage from your battery is going to provide the same amount of pressure through each one of these circuits, okay? And if you have a large enough battery, you're going to be able to provide the same pressure and you're going to have a lot of current so that it can flow. So in this particular situation, we have a current draw from the SS3 pod of 1 amp, and then we have another 1 amp, and then we have 10 amps for the light bar. So the two pods draw a lot less power because we have 1 amp times 12 volts. So right up here, if we just were to do the loose math, this is 12 watts. 12 volts times 1 amp, 12 watts. Now, if we look at the light bar, we have 12 volts times 10 amps, 120 watts. So the light bar requires much more power than our SS3 pod. Now, if we were to put two things in series, let's say we did two SS3 pods, they require the exact same amperage to run, but they also need to have 12 volts in order to turn on. So what happens is, if we take these two pods and we connect them in series rather than in parallel, you're going to have a 12 volt to 6 volt drop, and then a 6 volt to 0 volt drop. And that's a problem because we don't have the 12 volts that they both need. They both have 6 volts, which is a problem. So that's why we connect them in parallel. And down here, I just also explained how the math works for the SS3 pod and then also the Diode Dynamics light bar. These are numbers straight from their website, and so I just wrote those down there. It looks like an SS3 pod uses about 15 watts, and a 30-inch light bar uses about 140 watts if you did more exact math and you didn't use the rounded numbers that I wrote down here. So another thing to just reiterate is when you have everything in parallel, they all have the same voltage drop across each branch of that parallel setup. But the current flowing through each one is going to be different depending upon what sort of equipment you have connected. So now this begs the question of, why is this not a good layout? Why can't I wire up everything just like this? And this is the reason why. Most switches, especially when we're looking at these DC rocker switches, they are rated for very low amounts of current. So you may be able to get away with something low powered like an SS3 pod, Sport Pod, because it has 1 amp. But you're going to all this work, so you might as well wire it up correctly to where you're not going to have any issues. So if this switch can only, let's say, stand 1 or 2 amps, we need to figure out a way to still use this switch to power our light bar, which requires 10 amps. If we were to just put our switch right here, 10 amps would flow through our switch, and then it would burn out. Now again, remember, amperage is the flow of electricity, 12 volts, or that voltage, is the pressure at which that electricity is pushing on the top of this circuit. So let's jump into an example that's a little more applicable to the setup where we're actually putting this inside the plastic. So this is kind of a basic circuit regarding some sort of equipment you want to set up on, let's just say, this one rocker switch, okay? Don't be overwhelmed. This looks like a lot, but it's not really quite as crazy as you may think. So what we have up here in the top is we have our 12 volt DC battery. This is our car battery. So the positive terminal is going to provide power to a bunch of different things, and the ground terminal is going to be connected to the frame of the vehicle in some location. Now I will mention this is something I learned the hard way, or at least just had to do a little research on myself, is make sure your ground is touching bare metal, not some sort of clear coated metal or painted metal. It's not the same electrical connection. Make sure it's connected to bare metal. Now for the first example, it's pretty simple, but I'll just show you. What we do is, in case there's any sort of issue with the circuit, we always put a fuse. Now, all a fuse does is basically break the circuit if too much current flows through. So let's say that this fuse is a 10 amp fuse, okay? If you've seen a fuse, a lot of times they look like this little staple or something, right? They've got 2 teeth on them, and you stick them into those fuse boxes all along your vehicle. So if we have a fuse like this, 10 amps will flow through here just fine. We have maybe 3 amps flowing 5 amps flowing. A lot of times on the top of these fuses, it will be written as like 10 amps. Now what happens is let's say we have 15 amps flowing through this circuit. There's a little metal piece right here that sticks down through there, and that will basically cut itself. And what that does is it prevents electricity from flowing through this circuit any longer. So a fuse is a really nice fail-safe, because this will cut off the power right at the top, right at the source. You don't want to put your fuse at the end of your circuit, because then it's not doing anything. And so if all of a sudden you have a problem with the electricity flow, hopefully it prevents you from frying this Blue C's USB block, for example. Because this is probably rated for 5 amps or 7 amps or something. And like it says on the front of the block, it's got this 4.8 amp source amperage. So we don't necessarily need to know the exact numbers here, but it's important to pick the correct fuse size, because if you go too big, it may allow current to flow through here that is harmful for this Blue C's USB block, but it is never going to actually break the fuse because you pick too high of a number. On the contrary, if this is requiring, let's say, around 5 amps to operate for a 4.8 amp output, that means 5 amps of current is flowing through here. And if you were to pick a 5 amp fuse, there may be small spikes or something in the electrical flow that would cause this to break, and it's really nowhere near the amperage that's being used for this that would cause some sort of harmful activity in this block. So you'd probably pick like a 7.5 amp or something to put in this fuse. Maybe even 10 amp would be fine. It's all going to depend on looking at the specs of your little USB block and making sure that you always are staying under, or at least around, the operating current of this block. And then that would go straight to ground. So this right here is an example of how I would connect my Blue C's 4.8 amp block right here to a fuse on my Blue C's fuse box, which is drawing power straight from my battery. Now, let's jump over to a slightly more complicated example. So, like I was saying before, this switch right here, it can't withstand a lot of current, but we need a lot of current to supply to our light or whatever sort of equipment you're using. Maybe you have an air compressor, maybe you have a cooling fan, maybe you have a light bar, whatever it may be. You may need much higher current, like 10 amps, to power it, but you can't run that power through your switch. So that's where a relay comes in. So what I have drawn up here is we've got 2 different fuses. We've got power coming from our battery going through a fuse that goes to our relay. So this 30 number right here is the power feed from the battery on our relay. These numbers are often written on most relays. And then over here we have another fuse that is the power source to our switch. And our switch, let's say our switch can only operate under, who knows, maybe 5 amps. We'll just say 5 amps. I don't know if that's the perfect number or not. And then over here we have a fuse that maybe operates under 30 amps. Because maybe we want to hook up, a big set of SS5 lights from Diode Dynamics, and they're total beasts, and we've got a bunch of lights and we want them all on the same power, so we put a 30 amp fuse in there because we're going to be flowing electricity like crazy. So we've got a 5 amp fuse here, and we've got a 30 amp fuse here. So the 5 amp fuse limits the flow of current into our switch. So this switch is not going to get blown because this fuse protects it. Now this switch has 3 different ports on it. Remember, we saw that on this little piece of paper from Blue C's. 2 is our power feed, 3 is the load or output of our switch, and 7 is our ground. What the switch does is it drops a little wire between 2 and 3 that allows the power flowing here to go into our relay, okay? So now jumping over to our relay, we have 5 different ports on our relay, okay? Now the relay has the 30, which is the feed of the power from the battery. Then we have this port number called 86 This is called your positive feed trigger. This is going to be a voltage signal from your switch that tells your relay to turn on, okay? 87A is a port on your typical 5-pin relay that you will typically leave as an open circuit, and I'll explain this in a little bit. Then we have 87 port. 87 port is where the output of your feed is going to go once your relay turns on. So this 30 feed here from your battery is going to flow from your 30 port to your 87 port once 86 is turned on. And then 85 is just your ground, and we'll show you that this ground is basically where the electricity goes from your 86 port. Your 86 port will flow to 85 when this switch is turned on, and then the 30 current will flow from here to your 87 and then down through your light or whatever you may pick. So then what basically happens is we have a protection for our switch and we have a protection for our light, because let's say our light can operate up to 30 amps and our switch can operate up to 5 amps. Awesome. You've probably picked a relay that can support 30 amps as well, because then both of these things can operate under 30 amps and the switch can operate under 5. So what you do is you're sitting in your rig, you're like, okay, I want my light bar turned on. You hit your switch and this little wire here drops in. This current flows through here, turns on your relay, and so all the current that's been right here the whole time now is like, sweet, I get to flow through. So the electricity flows through your relay and turns on your light. And this is how we can have a little 5 amp or whatever switch power a 30 amp circuit using a relay. Now, depending upon your light, this circuit may be much different amperage, so you're going to still have to do your research on what type of lights you're running, what sort of wire size you need to run so that you can run this much current. Because remember, for any sort of wire, you've got your insulation and then you've got your actual metal in the middle. And just here's an example. If you have 30 amps of current, that's a ton of electricity. You need a really big metal piece in the middle of your wire so that all the electricity can flow. It's similar to if you turn on a water hose or you turn on a fire hydrant, you wouldn't go hook up your favorite Wendy's straw to the fire hydrant. You need to hook up something huge, like, you know, those big fire hydrant hoses are ginormous. And if you were to hook up a Wendy's straw to your fire hydrant, that Wendy's straw is going to get obliterated. And so you don't want to do the similar thing of hooking up a small wire to something where there's so much electricity trying to flow. So that's basically everything you need to know about relays and switches and picking the lights. And most lights, they just have a positive and a negative. And so that's how you'll turn on the light. Sometimes these will also have another connection that's like your DRL light. And a lot of times your DRL is just going to be fed by some other fuse from your vehicle. So let's just give a quick example on this because I forgot to mention it. What you a lot of times will do is you have an INJ fuse on your vehicle. This is the one used for my Alpha Rex headlights. You've got an INJ fuse, we'll write fuse here. And this probably has a feed from your battery. And then right here, this is where your starter is. So until you actually put your key in your starter and you turn on your vehicle, this INJ fuse is not going to get any power. And so what happens is you turn on your vehicle and then your electricity flows through your INJ fuse. Now, a lot of times these fuses are pretty small. They can be 5 amps or they can be 10 amps. And so not a lot of electricity really flows through here. So you can't just use fuses in your typical fuse box under your hood because they don't have the power output necessary to operate these lights. But most DRLs, if you look them up, they're sometimes on the order of 0.1 amps or 0.01 amps. They're very small currents because they only typically have a few LEDs, and it doesn't require much current to operate a few LEDs because they're just much smaller than your typical light bar. So that's how a lot of this kind of works and operates. I do just want to jump into one other thing. So if you look at a relay, or if you look at your fuse block, to kind of explain, you know, you've got a fuse here, you've got another fuse here, holy cow, a lot of fuses, what's all going on? So what you typically will have is, on my particular rig, I've got my battery, and then I've got this huge inline fuse coming off my positive terminal that I think is like 60 or 100 amps. It's a ginormous inline fuse. And then that feeds power to my Blue Seas. So this is my Blue Seas 6 fuse. Okay? And so once we have this huge fuse protecting our Blue Seas fuse block, this can operate at a max of 100 amps. So that means you really don't want to put an inline fuse up here larger than 100 amps. If you go smaller, it's just going to pop sooner than what you probably want. So you typically pick your fuse to be similar to your equipment. Now, all this fuse block does is it basically is like a splitter. You've got a bunch of power coming in that if all of these circuits are turned off, the power just keeps on flowing to ground. But if you have power that's actually turned on, sometimes you're gonna start feeding circuits. So this 30 amp fuse, like we had drawn in this picture, might be for an LED light bar. This 30 amp fuse might be for a set of pods. This 30 amp fuse might be for a second light bar. This 7.5 amp fuse might be for like your USB adapter. And then maybe you've got a communications radio, and maybe you've got something else. And so all 6 of these circuits operate off of these rocker switches. So what you just have to make sure you do is this draw can never exceed 100 amps, because if you try to do that, you're just going to start popping fuses. And so this is essentially, though, all a fuse box does is it helps to divide out that current, and then you have little safety circuits, and it's just a very succinct, you know, clean way to collapse all of these fuses into one small location, rather than needing to have to do a bunch of inline wire fuses that are hard to find and hard to replace. You can just pop the little cover off of this and put in new fuses if you ever blow a fuse for some reason. And just to mention too, you should probably always keep a little bag of fuses in your glove box or something, so that if you ever have an issue, you can put a couple more in. Now, for some of you that are maybe curious on what a relay does or how it works, I just wanted to draw out kind of a little example circuit of a relay. So we talked about some of those different ports that are on a relay, and you can buy relays in 4-pin and in 5-pin orientations. So for example, on this relay circuit I have drawn out here, this is a 5-pin connection. So we have our 30, our 85, our 86, our 87, and our 87A. Now 30, that's our feed from the battery, or from that fuse that was that 30 amp fuse. 85, this is going to connect straight to ground. We've got 86, this is our switch feed from this switch. So when this turns on, this is going to run current into our relay, and it's going to come in right here. And then we've got our 2 other ports, our 87 and our 87A. So a lot of people leave our 87A an open circuit because they don't want something turned on all the time. Because what happens is when you turn this switch on, it runs electricity through this coil, which basically attracts this little switch arm here in this direction, okay? And so what happens is 87A was turned on, and then when you turn on this switch power, this coil has electricity flowing through it, and it sucks this little trigger or switch arm to this side, and now the battery power can flow through 87, which is probably connected to your light. So a lot of people call this the normally closed pin, and then this is the normally open pin, because when your relay doesn't have a switch turned on, this would be the normally closed position, this would be the normally open position. And so 87A is typically just an open circuit, because that means that no current flows through here at all when you don't have your switch turned on. And so what happens is when you look at this circuit right here, we'll just zoom out here a teeny bit. If this is a completely open circuit, which means that this is like broken right here, let's just say, because your pin is stuck on the 87A, which is connected to nothing, no electricity will flow through here at all because the resistance is incredibly high. Remember what we talked about with the pressure, where we have voltage on one side and ground on the other. There's like no pressure on one side, so everything wants to flow. But let's say we've got an open circuit over here, so it's just pushing like crazy. No matter what sort of voltage we put over here, this ground is always going to push it back. And so that's what's going on right here when the circuit is turned off. And so all of your electricity when this circuit is turned off is probably just going to flow throughout the rest of your circuit. So in a nutshell, that's really how a relay works. These resistors are typically very large, and so if you have a switch with a 12 volt signal coming through and your resistor is very large, remember our voltage equals current times resistance. So if we have 12 volts here and resistance is really, really large, our current is going to be very small, which is exactly what we want because these switches can't really tolerate a ton of current. So that's how we limit the current flowing through our switch, but then really maximize the current flowing through our relay. So those are some of the things that I learned when researching relays and switches. I just wanted to create sort of a summary document, so to speak, of everything I learned. And if some people were trying to do research, they could at least look at how I did my wiring, and maybe that would help them in some way with the research that they are doing. But like I said before, this is just for entertainment purposes. I'm by no means a vehicle wiring teacher, and I just wanted to basically say my side of the story when wiring up my vehicle. So thanks for listening to this. I hope I wasn't too long-winded, but I just wanted to cover a bunch of the details that I learned when I was doing my research on how to wire up a vehicle. So just to give a little bit of direction as to where we're going, I have all the switches installed. These little blue squares are lights, and so when you put these stickers on that represent what the light is for, then it will light up right here on the switch. So that's why I kind of like these lights, even though the fact that they're just cheap, which is nice too, but they also kind of have this nice sticker set that comes with it and everything. And it was like 3 for $17 or something on Amazon. I'll link everything in this video down below. And then this is going to be a port right here for a handheld mic from a GMRS radio. So I'm going to be putting in this little port here, which is for a more powerful Midland radio. But if you wanted to use the old kind I had a 2-pack of these Ethernet ports. And so this is an Ethernet pass-through. There's just an Ethernet port on the back and the front. So you can connect a Ethernet cable from this port to your Midland MXT 275. And then this you could put on this little blank right up front. So a bunch of different options. I realize if you have a limited, this is where your seat heaters are. So you might have to mount this in the lower tray by default. It's so similar on the top and bottom that you could very easily still put this down below. I got everything glued up, as you can see here on the back, which is just a plastic to plastic JB weld. And then I soldered this wiring harness to hook up my USB port. So we'll go through all of this in the next video, but I just wanted to give you a little teaser for the end of part 1. Alrighty, well, thank you so much for watching. I hope I didn't go too long on this video, but I wanted to cover a lot of material, and I'll catch you all in the next video and hopefully in part 2.